Okay. We're going? Okay. Yeah, so welcome back. Sorry about the late start, I guess. OBS is bad. But yeah, we're gonna be continuing. I keep wanting to say last week, so if I say last week, I really just mean the week before spring break. But me and Zach, we're gonna be continuing kind of our little block on binary exploitation. So same ground rules as last time, still using x86 assembly, Intel syntax, 32-bit instructions registers. And again, we're using the same VM as last time. So if you have that, that works fine. If you don't, the link should be up there a little bit. But the labs we're using are in the announcement we put out, I think, yesterday about the meeting. Again, you'll have to copy those over using some kind of like web tool, like wormhole thing, because copy and paste is disabled between the VM, your host machine. So yeah, some of kind of what we'll be going over today. So from the last meeting, we figured out how to use buffer overflows to kind of hijack the program flow. So, manipulating it to where the program could execute functions that weren't supposed to be there, or change variables that normally wouldn't be able to be accessed. And while this is something that can be useful, it's not always the most useful because, again, I mean, who's going to put a function in their program that's like, oh, this function does something really bad and should just never be run, but it'll just be in here for no reason. So it's something that is useful, but it's when we're talking more real world applications, not as in obviously buffer overflows are still very important, but they could sometimes have a bit of like a limited scope of what you can do. Which we can, but we can use kind of the concept of how buffer overflows work to kind of get more out of the program that we're trying to exploit, such as like shells or remote code execution, which both those things are very bad and very advantageous to an attacker if they can get that out of the program. So the first thing we'll kind of be going over is a type of attack called return-to-shellcode, and this is actually using a executable program to pop a shell. So kind of what is return-to-shellcode? So again, we're kind of using control flow hijacking, essentially just putting kind of an official name to what we did, again, kind of 2 weeks ago, where we attempt to overwrite whatever is supposed to go into EIP. If you remember, that's the instruction pointer register that points to where the next instruction to be executed is. So essentially, we're trying to find some way to overwrite EIP to point it wherever we want it to do. So last time we did this, overwriting the return address of a function to point it to some other address, other function in the program that we wanted to run. But in this time, instead of pointing to some function that's already there in the program, we're actually going to be pointing it to our own shellcode that we're going to be executing. And when we'll point it to that shellcode and execute that to give us a shell. So yeah, they essentially, pretty much the definition of a return to shellcode attack is it's manipulating the program flow to give us code execution. So we insert our own set of instructions into the buffer, point EIP to those instructions by overriding the return address, and then this results in our code being run. And typically this is obviously by the name shellcode, return to shellcode, is used to get a shell, but again, you can have the code do other things if you want it to. Just shells are kind of the easiest way to learn that. So essentially what a return to shellcode kind of attack does, it essentially changes the return instruction to function instead as a jump instruction. Which, again, if you're familiar with that, instead of a return does all the stuff with the stack where it cleans it up and goes back to previous stack frame, whereas a jump just says, here's an address, go there, and run whatever's there. So if you remember from last time, we kind of had this example of we were copying stuff into the buffer. So we have here, last time we had our your return address got overwritten by the last bit of what's in the buffer. And so whatever is there will be loaded into EIP whenever that ret instruction is called. So essentially what we can do is if we pass something to the buffer where we pass, a bit of padding to make it there, to like pad out the stuff that we kind of don't care about, and then put the address of where our shellcode starts, where the return address was, and then put the shellcode somewhere in the stack, we can basically point it to when the program tries to go through, pop that return address off. It just is the address to our shellcode, and we'll end up running our shellcode. So yeah, here you can see EBP gets set to some random value somewhere else that we kind of don't really care about, and EIP gets moved now to from wherever the actual instructions for the program are, and now is executing stuff in the stack.
One thing I'll add out is that notice in this example, the shellcode is technically like at a higher address than your return. So this is like, it's not, in this example, it's not actually inside the buffer. It's just like kind of above somewhere in memory. And that's a useful strategy because a lot of times if you have a very small buffer, your shellcode won't fit there. But if you have a big enough buffer, you can essentially do the same thing we did last time, like where you just put, like rather than putting where those A's are, you could put the shellcode there and point back into the buffer itself. But that's only if your buffer is big enough. But yeah, that's just something.
In this case, yeah, like our buffer was essentially like 4 bytes, so that's not shellcode. I think the shellcode that we provided you is like 80 bytes or something. It's like 70 or something. So it wouldn't fit there. I guess I don't know if there's necessarily a downside to doing it this compared to normal. I mean, the one thing with this is obviously with the way the stack works is putting the shellcode farther up the stack here will basically just overwrite like everything past.
Yeah,
like it will destroy a lot more of the program to where like if you try to exit the shell, the program is just going to be basically completely unsalvageable.
Yeah, that's exactly that. The buffer, it's much easier to restore the state of the program, like make it function as intended after you exit the shell. But if you have like 80 bytes of shellcode just overwriting random things,
you're gonna destroy your stack, your previous stack frames.
It kind of depends on or do you just want the shell. Like,
yeah,
if it's something that needs to like appear to work correctly, then you might want to rethink that approach.
Yeah. So one thing that's kind of important for return to shellcode attacks is something called a NOP sled. So kind of the main concept with this is a lot of times it's knowing exactly where the shellcode is kind of difficult. Obviously, whenever you call a function, the whole stack frame moves. So depending on where you're calling your shellcode, it can be sometimes difficult to pinpoint exactly on the stack it is. And plus two, like obviously in our case, this is a very ideal scenario. We have the source code, we have the executable, we have our own environment. We could run it as much as we want, look at the internal state as much as we want. You can't always do that with like obviously real world programs. So it's plus two, even in our case, in pointing to a one specific address where the shellcode starts, then you have to go through like, constantly look at the stack, determine exactly where your shellcode is, make sure it lines up nicely with an address. Like it's just kind of a pain. So basically what you can do is probably most of you are familiar with a NOP or no operation instruction, which is essentially just an instruction in assembly that does nothing. It usually just does like some bogus instruction like add 0, 0 or something. So essentially what a NOP sled is you put a bunch of NOPs into the buffer somewhere before your shellcode. So basically the idea of it is you try to point the instruction pointer just somewhere in your NOP sled. You don't really care where exactly you hit it, but now you have, instead of, specific address, you can hit anything in a range of 100 addresses. And as long as you hit somewhere in that, it'll start executing those NOPs and slide down to where your shellcode is. So this is essentially what it would look like on a stack. You put your EIP where you want your EIP to be, where the return address is, overwrite that, and basically you'll just have a bunch of NOPs up there somewhere in your buffer. And then you'll just want to point the instruction pointer somewhere in the knobs. Again, the main advantage is it gives you a lot more leeway in that you don't have to know the exact address of your shellcode. You can just point it somewhere close enough and it'll get there.
That we kind of prepared because the VM is set up like it's pretty easy to just point directly to the shellcode, and for the context of like the labs that we made, just because everything is a very tightly constrained environment to be like exactly the same every time. But like in an actual like real life environment, you would definitely have a knob sled and hit in that.
Yeah, which even with our lab, I would probably recommend just doing a knob sled because again, it just makes your life easier. Like it's.
If you just see like a bunch of knobs, like where you're.
Yeah. You could just like put some address somewhere in the knob, so you don't have to worry about like, okay, count over and yeah. So yeah. So that's pretty much how return to shellcode attacks work. It's not super complicated. It's basically just buffer, like kind of the standard buffer overflow thing we did with just the extra step of now you're running your own code instead of someone else's code. So yeah, so now we're going to talk about another type of attack called a return-to-libc attack. And with this is a lot of, again, we have been operating in a very, very ideal environment. Basically, all protections turned off, everything super static, very easy. Like real world, it's much, much more complicated, and there are a lot more defenses in place to mitigate stuff like buffer overflow and like shellcode injection stuff. So most like modern operating systems, compilers, pretty much everything will have measures in place to prevent code from running where it isn't supposed to. And probably one of the most common ones is DEP, or data execution prevention. So essentially what it does is it goes through memory and it marks sections of memory as either code or data. So sections that are marked as code, those are the only sections that it will let execute. And then sections marked as data are marked as non-executable. And if something tries to run in there, it'll yell at you and like basically just crash the program. And this is typically one thing is the no execute or NX bit. You may hear that thrown around occasionally with DEP a lot. It's basically just a hardware implementation for allowing DEP to work to where marking memory is executable or non-executable. So essentially, kind of our previous example, if we try to do this return shellcode attack now, but now say we have DEP enabled. So it'll happen. We'll have our inject our shellcode onto the stack. Everything should be fine. And when the ret instruction will happen and try to point to where our shellcode is and start running it, it's just going to crash. The program's just going to say, like, I don't know, would it just segfault, I guess, probably? Or yeah, it just have some kind of error because it's marked this whole section. All the stack is just supposed to be data, like local variables, all the addresses and stuff. It's just data. So it's trying to run code. It'll yell at you and it'll crash. So return to libc is a way to get around DEP. So essentially what we're doing is we're using built-in C functions that are already imported by the program. So since these C functions have already been imported, they're already in memory, and since they're imported by the program, they're marked as executable because they're legitimate functions. So essentially how return to libc works is, whereas shellcode, we're basically changing the return instruction to act like a jump instruction. With return to libc, we're essentially going to change that return address instruction to act. We're basically going to set up the stack as if it was a call to that function. So yeah, this is essentially what the stack kind of looks like. On the left here, we kind of have the stack set up as if it was a normal function call where, you have your local variables for your first function, and then you push arguments for the second function, your return address, and then your EBP. And then you have, right here would be, and down would be your function 2's stack frame with all its local variables and stuff. And basically, once we do a return to libc attack, on the right here is what the stack will kind of look like, where we have our buffer. We just put in some padding to overwrite the old EBP because we don't care about that. We put a function pointer where the address of the C function that we want to call. We put a little bit more padding to wait, why do we put the padding there again? It's oh yeah, it's because the
expects the return address to come before the variables. Like when it's parsing up the stack, you have to have so like in that padding, if say you wanted to have like a clean exit, or that like the lowest padding is here, you could put like the address for like exit, and that's what it would return to after it finishes your libc call.
Yeah, and then essentially, yeah. So you have that there, and then you just put the arguments you want to pass to that function. So this is just kind of a basic example of it. So here we just have a like function, main function that just defines a string and then basically creates a pointer. Command is essentially a pointer to the string bin ls, and then we pass that pointer to the system function. So here we have our stack. We'll push the pointer to that bin ls string and then call system, which will push the return address of where we're supposed to go back to. And essentially, like on the left there, that's what it looks like with a normal, again, a normal function call. Whereas on the right, if there was like a buffer that we wanted to insert, like perform a libc attack with, obviously, again, you have the buffer, you have the padding to overwrite the old EBP, then you have the address of wherever system is in that program, and then the padding, again, you can put the address of some other function if you want it to exit cleanly, and then whatever you want we put, in this case, it would be, we want bin ls to get executed. So we put that command. Now, the one thing that is important with like most C functions, like stuff like system or execv, is you're not actually passing the string directly to the function, like on the stack like this, like command. It's just a pointer to that string, which again, I think most of you understand how pointers work and stuff. But
And that's kind of a challenge because depending, like, so the way a string is like defined C is like you have some ASCII characters in the null terminal, right? And depending on how it's taking input, a lot of like ways in C, they don't allow you to put a null byte as an input. So like one strategy is put the string you want to reference in your buffer and then like reference it, but you have to have it followed by a null byte, and so like that can get kind of tricky. It's possible depending on like how it's doing. There's some tricks to it, but we'll show like a better way. There's a couple of different other ways.
Yeah, because sometimes strings will be already baked into the program, and there's a way you can actually search for those in GDB. So yeah, so that's pretty much how libc works. Again, both those types of attacks and methods of getting shells are not super complicated if you kind of understand how buffer overflows and the stack works. But it's just good to get an overview of them. But yeah, so again, we've been operating in a very, very ideal environment. Like again, the stack is super easy to look at. Everything's completely static. We can do whatever we want. I mean, we have the source code. We can run the program as many times as we want to. There's basically we can pretty much do whatever we want. Again, the real world is much harder, and there are a lot more defenses in place. And there are still ways to get around those, but it's definitely a lot more complicated than just look at the stack, and once you figure out, how much padding you need in the buffer and like where the return address is, you're good. It can be a lot harder than that. So Zach's going to talk about some of the other types of defenses that are kind of implemented more.
Yeah, so the first one is ASLR, address space layout randomization, and kind of our assumptions thus far is that we make the assumption that we know where like the buffer is in memory, like where the stack is in memory, so we can reference it. And we also are assuming that we can reliably, like for libc, we can reliably get the address of functions baked into memory, right? And so when ASLR is not on, so if it's off, then everything kind of is organized the same way every time you run it. But ASLR essentially randomizes like your stack, your heap, and all this is at a different position in memory every time. So you can't just reference the same position and expect it to work. So this is like pretty much this is enabled like every operating system. And so it makes things much harder. There are some ways to get around this, and it's kind of complicated, but you have to rely on a memory leak or something, some other vulnerability to give an indication of where things are in memory. You can build off of that, but that's like a little outside of the scope of what we wanted to cover. It's kind of like intro kind of course thing. So that's ASLR. The other thing that's kind of like a very simple solution to some of these problems is all these attacks rely on overriding the return. So what if we just use something to check if that space has been, the space between the buffer and returners has been modified? And that's essentially a stack canary. So we put some random secret value on the stack in between the buffer and your return address. And essentially before we return, check, did the canary get changed? So if you overwrote, if you just like your padding, like we've done in the past, if you just overwrote that canary value with padding, obviously that will not be the same as whatever secret value we set it to. And so we know, okay, someone is modifying things where they shouldn't be, and you can react accordingly. You could just exit, or you could throw some error, whatever. So that's a very simple kind of solution, stack canary, but that can be overcome. And that's one thing I want to talk about is a buffer overread. And it's essentially like a buffer overflow, but in reverse. Rather than writing more data than you're supposed to, you can essentially read more than you're supposed to. And that could be used to defeat a stack canary. It could also, maybe be used to defeat ASLR if there were memory values on the stack, and you could overread and read some of those values. But the most famous example is Heartbleed, which is like a vulnerable version of the OpenSSL library. And essentially, how that worked is one machine would send a request message with like some arbitrary payload and a payload length. The second machine to kind of act that it received that, it would just echo that same message back to the machine one. But the problem here is that machine two just decided to trust the payload link without doing any verification. So essentially, you can give it a payload link that's much greater than the actual payload you sent and get the second machine to send more data than the size of your payload, and leak adjacent memory. And I have kind of like a simplified example. So like say if our payload's test, that's 4 bytes, right? I say when the payload length is 100 bytes, well then when the machine 2 responds, it's gonna give me my 4 bytes of test and then like 96 extra bytes. And so whatever is adjacent to that buffer memory is gonna get leaked. And so that could be a stack canary. Who knows what kind of secret stuff could be in there. And this is a problem, even if you do some form of checking on the payload link, that can still be a vulnerability, because there's things like integer overflow, integer rollover, because you have like unsigned integers, so you can like use like negatives, like trick the program into like thinking the number smaller or larger than it is. But in the case of Heartbleed, I think it literally just didn't do any checks. Like it literally just trusted it, and that was like a major vulnerability you'll probably hear about. And one kind of last thing to wrap this up that I'll just talk about that we didn't hear, another type of kind of approach to binary exploitation is what's called like ROP chaining. So essentially that's just like, for return-to-libc, we're relying on there being some C function that we can execute that's already like baked in. And ROP, or return-oriented programming, is kind of the idea of let's just find like random bytes throughout the program that can build the instructions we want and kind of like chain them together. So that's another thing, if you're interested in binary exploitation, you can look into on your own time. Maybe we can cover that later in the year if we want. But that's just like the last kind of major thing we didn't get to mention. But before we move into like the lab time, there's a couple more GDB tips I wanted to give. The first thing is, so when we talked about return to libc, we said that you need a pointer to a string. And so there's like 3 kind of approaches that I've seen. You try to write the string into your buffer and point back into your buffer. But like I mentioned earlier, that could be problematic because you need a null terminator, a null byte as like the string terminator, and like certain ways of input, like they won't just like let you input a null byte, like they'll just get cut out when you try to push that as an input. Another approach is to use environment variables. So if you set an environment variable to whatever string you want, then that environment will be loaded into memory and you can access it that way. But that's not a like super consistent method, because that kind of varies based on the OS and kind of other things going on in the operating system. But one surefire way to do it what we're suggesting is just finding strings that are already loaded by libc. So like to get a shell, you don't even need any external things. There's a lot of commands and stuff that are just already exist within libc itself, and you can actually find them using GDB. So I'll just show a little demo of that. Go to John's. Is this already up? Okay. So let's see. If I just do like GDB, I think it's what, target 5.
Target 5.
So the first command, this is info proc address. Wait, is that the right command? Oh, map, not address. Okay, info proc map.
Wait. Oh, don't you have to do .slash?
Oh, you're right. You shouldn't have to do. I think you can just. I think we need to run it as the problem.
Oh wait, yeah, you're right.
I don't have a breakpoint set. Okay, so let me just do this AS main. It's vulnerable. So I'm just going to set a breakpoint after vulnerable, just to show an example. B star. Yeah, so this one. So you do have to have a breakpoint set. All right, so now we set a breakpoint. I can run it. Oh, I need to command that. So now that we're at a breakpoint, if I run info proc map, this actually lists the memory address for the processes that are loaded. I don't see. Did you see libc when you did this one? Well, anyways, we can search through this. So if I wanted to find something, if they have a start and an end address, so I can just pick like this start address. Just pick the greatest one as my end address. And then I can search for a string. We'll just try like that. So I don't know if that's. So basically what I did is so with the find command accepts a start address, like the starting address of memory to search for, and then an end address. And all I did is I just took the first start address and the last end address that's in like the same range. It's like this 80 to 811 range, and I searched for the string test, and you can see it gave me this address. And essentially, what this means is that the string test exists in memory at this address, and you can verify it by doing x\s and then the memory address. If I do that, it'll tell me like at that memory address is the string test. So if you want to find a command, you can use this find thing to just find command to like find like, you know, bin bash or bin sh or whatever you want to like pop your shell. And all this is in the slides, but I just kind of wanted to show how it worked because it's not super intuitive sometimes from the slides. But other than that, you will need to use Python for this. For the payload, like the last few labs, like you could definitely just do by hand if you really wanted to. This one we heavily recommend that you use Python 3. Inside the VM we gave you, there is a shellcode.py that you can just import, like from shellcode import shellcode, and that is guaranteed to work. Like that is working shellcode. The other thing is, in all of these labs, the GUID bit for like root has been set. So like all of these.
We're trying to pop a root shell, basically.
Yeah, so like all the executables have been set. So like no matter who runs it, it runs as root. So when you do like bin sh or bin bash, whatever, it's gonna pop as root. But in the real world, that may not always be the case.
Well, in the real world, you probably should not.
Yeah, you should
not set that on a program unless you have a really, really good reason to.
So like that's why you'll get a root shell if you just pop any sort of shell, but regardless of the user you're running the executable as, it'll pop a root shell. But yeah, so main thing is use this shellcode. It's guaranteed to work. I mean, you can try your own shellcode if you want, but it'll be this shellcode is guaranteed to work. If you point to that shellcode and get that to execute, it will pop a shell. So but yeah, now we have 2 labs. We have target 4 and target 5. You will have to download them. They're not already in the VM, but we put a link
in the Discord for you to download like a tar file with these two labs in them, and you can use web wormhole.io to transfer the, like, when you download it, to transfer it to your to the VM. You have to sign in on the MacBook if you're using one. You have to sign into your Wi-Fi, but you can delete the credential afterwards. Because the default homepage in the VM should be like on Firefox, should be webwormhole.io. So you can use that to download the tar, and then you can, do target 4, target 5. So target 4, this is a return to shellcode. Dep is not enabled, so you can just put shellcode in the buffer or wherever you want memory and point to it, go. And target 5, dep is enabled, so you'll want to do like a return-to-libc attack. And so I guess we'll just give you guys some lab time for you to ask questions as we go. Yeah, we can. And these slides should be available. So, like, if you want the Python, and then I add a couple more GDB commands and like how to find the strings. Right.
Go over the solution for target 4 now, which is the return to shellcode one. So open this up in GDB. I guess we'll first look at the source code real quick. So we have very simple here, just basically main. We call some function vulnerable that literally all it does is copy our buffer, copy our input into a 100-character buffer, and that's all it does. A very simple program, does basically nothing, but it's enough for us to get a shell on. So let's open this up in GDB. Probably look at vulnerable first, because that's typically, I like to put a breakpoint. She's right here. This function is always there, so this one kind of doesn't matter. And even though it's not labeled, it's the only other function called, so we can assume that this one right here is like most likely stir copy. So we want right after that, we want a breakpoint. So that way we can see what's in our buffer whenever we pass stuff in. We'll set that there. And then, yeah, so let's just try running it with some A's. And then look at the stack. What is it? X. HP. Nope, that's wrong. I forgot the X. Oops. There we go. Okay, so yeah, here we can see our A's showing up on the stack. This, to me, it looks like all this right here is our buffer, and then we have, I don't know, some old value on the stack that's probably not necessary, and then probably where our old EBP is. And then this kind of looks like a return address. So I can double check this by doing disassemble _main. If I go to where vulnerable is called, you can see this address here is 49D70. And you can look right here, and we have 49D70. So this is indeed our return address. So as far as getting to pop a shell on here, so we know our buffer size is 100 bytes. So if we just pull up our solution here. Let's see, how did I do this actually? Okay, yeah. So basically here we just have some amount of padding. Honestly, this could have actually all been NOPs. I don't see any reason why it couldn't be, right? I don't know why I put padding in here. I think it was, I don't know. I was just doing that. But so basically we'll just put some amount of padding. Again, this could have all been NOPs. It doesn't necessarily matter. And then we put our NOP sled right here. I'm just going to put in 39 of them, which the shellcode is 53 bytes. So all of these together should be, I actually did it in the other way where instead of trying to, here on the stack, instead of trying to say right all the way up to here and then insert 4 bytes of padding and then the return address, I just did it where I'm like, I don't care about the old EBP and stuff. It's gone. Just write the shellcode up right to the end of up to where the return address would be. So in total, these two plus the shellcode should be 104 bytes, because that will be enough to fill up our buffer and overwrite the 4 bytes of whatever the old EBP was. And then again, we need to point our to override a return address, we need an address somewhere in this buffer. So what did I choose here? 95D0, I believe. Yeah. So I just chose that. It's just right here. Again, that's one advantage of a NOP sled is you can just kind of put it somewhere as long as it's close enough. Now if I run this with passing this in as an input, start it again, and we've hit our breakpoint. So now if I look at the stack, you can see that we have some padding here, and then 95D0. I actually did happen to hit it right where the NOP sled starts, just kind of how it was. But you can see right here, here's our NOP sled. So as long as I hit really anywhere in this range of addresses, our shellcode would execute. And again, that's the big benefit of a NOP sled. And then pretty much everything from here is all our shellcode. So this is all just, again, we gave it to you. This will just spawn a shell. And then this right here is where we overrode our return address to point back up here in the stack. So how do I continue again? C? Oh, well, I think that's gonna, yeah, that's gonna break because GDB is not going like that. But if I run 4, it's an argument. There we go. We have a root shell, which apparently it doesn't actually work. The root shell stuff may not work correctly if you're running this on your own VM and you just copied this. Yeah, I don't know. It just kind of is that way, I guess. It's kind of weird. In the future, if we do this again, I'll probably just give you the make file so you can compile it on your own. But it still should at least spawn a user shell from the program. So yeah. Okay, yeah, so here we have target 5, which this is, again, it says in here, it's compiled with dep enabled, so this is going to be a return-to-libc attack, because we could try inserting shellcode and stuff, but the program will just crash. It's not going to run. So essentially what we do is hold symbol vulnerable once again, infer this is string copy right here. So just copy this address, set a breakpoint there. And then if we actually look at the source code, which this is one thing it's just included, is they do have system here. So this function just, again, kind of doesn't do much, but you can see they're using system, and we can actually use system to execute Linux commands. As again here, it's using echo. But so if we can get it to execute a shell command, we can spawn a shell. But if you remember from the slides, we have to give it a pointer to a string. We can't just put the string there directly, because or else it won't work. So again, we could go through all the mess of kind of messing with null bytes, terminators, and trying to get around that. Or we can just see if there is strings already baked into here. Oops. Run it. Yeah, okay. Let's go proc map. This will show us stuff. And if we just do, find, do the first start address, and then the end address of this block, kind of what we did earlier, except this time we're going to look for, we'll look for what, bin sh, I think that's there. Yeah. think bin sh is here. Yeah. So we have an address now for where bin sh is. So essentially what we'll want to do is we'll want to construct our payload where we pad out the buffer, but then we call, well, one more important thing is we know system is here, but we also need to know where system is. So that way we can call system here, override a return address with the address of system, and then pass in this address right here as an argument to that. So that way it'll execute system with this as an argument, which is a pointer to bin sh. So it'll execute a shell for us. So if we open up our solution here, we can see here we have some padding just to fill up the buffer, and I think we're at the breakpoint right now with just a few A's, but if we XP, yeah, you can see right here. So I just put in a few A's, so that would be enough to overwrite here. And if I believe correctly, this is main's, the return address for main. So 22 A's is how many you need to overwrite the buffer and get to here. And then this right here is actually, so this is not necessarily necessary, I guess. Well, yeah. So we have our padding, but then here we have our address that we overwrite the return address with, which is the address of system, which is that 14D0, which is right here. And then right here, this part is the part that's not necessary is the exit address, which that's just so when we exit the shell, the program will just exit cleanly. So if I just do, you can see exit is in here. So we can just call exit, because again, the way stuff is set up on the stack is it will push the address of the function that you want to go to. Then next it'll push the return address for where it should go back to once it's done, and then it'll look for any arguments. So that's essentially what we're mimicking here is we're pushing the address of the function we want to call, the return address that it should jump back to once the function is done, and then any arguments, which in this case is that 884D, which is where that bin sh string is. So essentially here, all we're doing is we're just calling the system function, saying pass in bin sh as your command to execute, and then once you're done, call the exit function. So we run this. We get a shell. So yeah.